Hello everybody, my name is Andre Bauer, I'm from the University of Würzburg, and today I would like to present our forecasting method called Telescope. Before going into details, I would like to motivate our paper. Nowadays we are living in a fast-paced world. Due to the digitalization, new services or applications will arise. Some will get less interest and some will even disappear. Furthermore, the amount of connected devices will also increase. That means we have to face a complex workload in the future. One possibility to handle this is cloud computing, because it allows us a lot of flexibility. However, the management of the cloud, or more precisely of resources, is quite complex. Indeed, one could say we should use a naive resource allocation, but the cloud consumes 2% of the world's electricity and emits as much CO2 as the airline industry. For the sake of our planet, the resources in the cloud shall be supplied in an automatic manner and proactive. Current approaches observe the load over time, and based on this workload, they release or add resources. To be proactive, we have to know when the resources are required and how much. We get this information by performing time series forecasting, and there are different methods leading to different futures. Consequently, we need a reliable forecasting method to get the real future. Indeed, there are many forecasting methods in state of the art, and we compare here the methods on two different time series. On the left side we see forecasting methods from statistical field, and on the right side we see forecasting methods from machine learning. For example, on the left side, the gray line, we see T-bats on the upper forecast. Here it is not so good, and if you compare it on the lower forecast, this forecast may be the best one. We show this example because there is something called the no free lunch theorem. It says that there is no globally best forecasting method for all time series. That means if one tunes or optimize a certain method on a certain problem, it will get worse on another problem. To tackle the no free lunch theorem, different hybrid approaches have been proposed during the last years. The historical oldest group is ensemble forecasting. Here the idea is to use a set of forecasting methods, assigning each method a weight, and then perform a weighted forecast. The second group is forecaster recommendation. Here we have a set of training time series from which we could derive rules or an expert system which says which method is the best for a given time series. The last group is time series decomposition. Here the idea is to decompose a time series into its components, then forecast each component with its best method, and in the end all these parts are assembled together. Our method Telescope is also based on decomposition and can be classified in the last group. In our paper we pose ourselves two research questions. The first one is how to build a generic forecasting approach that delivers accurate forecasts while having a low time to result variance. And the second one is how to automatically extract and transform futures of a considered time series to increase the forecast accuracy. To answer these questions, we developed Telescope, that is a forecasting method based on machine learning that automatically retrieves relevant information from a given time series. And the second contribution is our broad evaluation. Here we compare Telescope against 9 methods, covering hybrid methods as well as established methods. So before introducing our Telescope approach, I would like to highlight some forecasting basics. One of these basics is that a time series can be decomposed in different parts. Some work decompose a time series in linear and non-linear parts. In our work we use STL to decompose our time series. STL decomposes the time series in trend component and seasonal component and ergo component, and these components can be additive or multiplicative. Indeed, there are some mixed forms, but in this work we stick to these two. The components, as I mentioned before, are the trends. The trend is the long-term movement of a time series. Season is a recurrent pattern like a monthly or hourly pattern, and the irregular part is a kind of noise that remains after the trend component and the seasonal component is removed from a time series. A further characteristic of a time series is that it can be written as a sum of sinus and cosinus terms, and in general, machine learning methods struggle with high variance and multiplicity within a time series. To handle this, there are a lot of transformations, and one popular transformation is the Box-Cox transformation, because it reduces both the variance and the multiplicative effects. And this is also applied because a simpler model may lead to a better forecast. Now I want to highlight the underlying idea of Telescope. Telescope consists of 5 steps. The first one is the pre-processing of a time series. In the second, features are extracted from a time series. In the third step, the model is built. In the fourth step, the forecasting is performed. And the last step, the post-processing is applied. Telescope is available at GitHub and it's written in R. In the first phase of Telescope, we pre-process the time series. That is, we perform a Box-Cox transformation to simplify the time series. We also estimate the frequencies of the underlying patterns within the time series, as we assume that the humans are controlled by the sun. We only consider frequencies like day, night, weeks, months, years, hours, and so on, and then we detect the most dominant frequencies for further investigations. In this step, we use information from the first step to decompose the transformed time series into trends, season, and remainder. Moreover, we use the dominant frequencies to extract the Fourier terms of the transformed time series. Before building a proper forecasting model, we first remove the trend from a transformed time series. This leads to a detrended time series that is a sum of the recurring patterns and the noise. Then we use the Fourier terms and the season to train an XGBoost model to reflect the detrended time series. As we don't use the noise as a feature, the model inherently learns how the noise is distributed within the time series. In this step, we forecast each part of a time series separately. The trend is forecast with an Riemann model, and the Fourier terms and the season part is continued because due to their definition they are recurring patterns. And then we use the future season and future Fourier terms and the XGBoost model to predict the detrended future time series. Then we add the future trend to the detrended future time series to get the future transformed time series. As the time series was transformed in the pre-processing step, we have to retransform it in the post-processing step. Therefore, we apply the inverse Box-Cox transformation to get the future time series. To evaluate our approach, we compare Telescope against different fields. The first field are statistical methods. Here we compete against ETS, seasonal ARIMA, and TBATS. The second field are methods based on machine learning. Here we compete against an artificial neural network, random forest, and XGBoost. And we also compete against hybrid methods. ESRNN is the winner of the M4 competition and is developed by Uber. Hybrid is a simple ensemble forecaster, and Prophet is developed by Facebook. Our dataset contains 400 time series. We cluster the time series into 4 different use cases, namely human access, nature and demographics, finance and economics. And for the evaluation, we took the time to result into account and as forecast error with symmetrical map. This table shows the forecasting error, more precisely the mean and the standard deviation over all 400 time series. Telescope shows here the lowest forecasting error and the lowest standard deviation. The second best method is seasonal ARIMA, and the worst method is RNN, the artificial neural network, and it has also the highest standard deviation. When we take a look at the time to result, here again this table shows the mean and the standard deviation. XGBoost achieved the lowest values, followed by Telescope, and if we look at seasonal ARIMA, that was the second best method in terms of the accuracy. It is almost 10,000 times lower than Telescope. So to sum up, Telescope achieves the best forecasting accuracy. The seasonal ARIMA has the second lowest forecasting error, but has the highest or the second highest time to result. ESRNN, that was the M4 competition winner and profit from Facebook, are tailored either to the competition or to the Facebook traces, and all machine learning methods show a worse error than the statistical methods. Before concluding my talk, I want to sum up. We talked about that forecasting is an important task for many decision-making fields, for instance in cloud computing. Unfortunately, there is the so-called no free lunch theorem, that is, that there is no forecasting method that performs best on all given time series. Therefore, a lot of hybrid methods have been proposed during the last years. We also try to tackle the no free lunch theorem by introducing Telescope, an automatic feature extraction and transformation approach for time series. And our results show that Telescope is able to outperform the other methods while keeping the time to result low and reliable. So these are the used references in the work. And finally, I would like to thank you for your attention. If you have any questions, don't hesitate and ask me. Here is my website, my email, and Telescope can be downloaded at GitHub. So feel free to use it, and as I mentioned before, if you have any questions, don't hesitate to ask me.